Hello and welcome back. Let's continue our discussion on the application of linear programming problem for waste management problems. Without further ado, let's get started. I've given a simple example. Let's take a look at that. We have to decide on the amount of municipal solid waste, which is MSW, generated by an urban region, and that is to be sent to two disposal sites, say X and Y. We need to find out the minimal cost of disposal at both the sites by satisfying the following constraints. The constraint number one is the total amount of waste generated is 500 tons, which means that both X plus Y or the entire solid waste generated in the urban region is 500 tons, and that must be sent to disposal site. So there's no quantity should be left aside, and all these things should be sent to the disposal site. And site X can only accommodate 400 tons. You can see at most, I've underlined that it's a keyword, which means a maximum capacity of the site X is 400 tons, and so was minimum the maximum capacity of site Y is also 300 tons, and at least 150 tons should be sent to site X. So this is an additional constraint. At least means when out of 500, at least 150, a minimum of 150 should be sent to site X out of 400 available capacity, right? And then the disposal cost per ton of municipal solid waste at site X is 10,000 rupee, and the Y is 15,000 rupee respectively. We need to find out the quantity of disposed stuff in terms of tons at site X and Y by minimizing the total cost of disposal or something like that. And you can also add an additional additional condition that the site is free, because when the site is fully occupied, then it's not possible to dump in additional thing. So but then you can understand it from this thing, 400 tons are free, the capacity is there or something like that. So any other constraints like the manpower requirement or the machinery requirement, it's just like overruled, because it is understood that we'll assume that it is there to effectively dispose of something like that. How do we solve this? We use linear programming for this, right? The objective function is to minimize the cost of disposal. So it's a minimization problem. Z minimum is equals to C1, the cost coefficient of X, which is the cost of disposal at site X, which is 10,000 per ton. Here is 10,000 per ton, and cost of disposal at site Y is 15,000, and that is why it is 15,000 into Y. And the constraints are the tons generated or the total waste generated that particular urban region is 500 tons, and that has to be shared X plus Y to both the sites. X plus Y equals to 500. This is an equality constraint, so will not make us much difficulty when we solve this by using simultaneous equations. But these things are inequalities. The site X can accept at most 400 tons, which means less than 400 tons. The maximum capacity is 400, but site X, I've made it 0, y, so it's understood. So I want to give it in uniformity. So X can only accommodate 400. Same as 0x plus 1y, which is this Y. The constraint of site Y, which is less than equals to 300 tons. And then we have additional constraint that a minimum 150 tons should be sent to site X. So minimum in the sense it is greater than equals to 150. And equation 3, 4, 5 are inequalities, and then that will make us very difficult to solve this by matrix method. So we use a graphical method for this. And before that there's a non-negativity restriction also. The quantity cannot be negative, so our lower bound is 0, which is X is greater than equals to 0 and Y is greater than equals to 0. The upper bound is positive infinity for both X and Y. So we'll solve using this problem. We'll solve this problem using graphical method, and this is the graphical method. So in the X quadrant, we name the site X, the quantity of waste disposed at site X, and the Y axis will make it the Y, the quantity of disposal at site Y. I have given 0 to 500. You can even give 1000, depending upon, by trial and error you can optimize the labels and the axis. And how do we get this 500 line? Is that the first constraint? Constraint number 1, x plus y is 500. When you substitute x equals to 0, we'll get y equals to 500, which is 0 comma 500. And when you substitute y equals to 0, we'll get x equals to 500. So 0 comma 500 comma 500 comma 0. This is 0 comma 500 and this is 500 comma 0. When you join two points, you'll get this perfect linear line. This is for constraint 1. And the constraint 2 is inequality, which is x greater than 400. I mean s less than 400, I beg your pardon. S less than 400. 400 is the maximum capacity. So that is why you can see in this inequality line. And in the equality line, there's no demarcation. And in inequality line, you can see that the region of our optimization is not maximizing this, but minimizing this. So our x should be less than 400, from 0 to 400. So that is why we get this inequality x less than 400. Can you try what will be the value for y less than 300, our third constraint? Y less than equals to 300. It will be like this. So y less than 300, the cutoff of y is 300, it's a constant for any value of x, and it is minimization, so it is beneath, so it is not above, it's the optimal region will be below this, from 0 to 300 in the y region, right? The next constraint is x greater than equals to 150. So can you guess how that will be? So this is 150 and this is x greater than 400, x less than 400, greater than will be the other way around. So you can see this. So can you guess where will be the optimal region or the feasible region where our solution lies? It will be here. When you connect these corner points, we get the feasible region. So our optimal value lies in this region. In fact, from the definition or from the theorem of linear programming, it will be the corner points or corner vertices. So it could be 150 comma 0 and 300, 150 comma 300, or it could be 400 comma 0 or 400 comma 100, or it could be 200 comma 300. So this 1, 2, 3, 4, 5 points our value. But the problem is the first constraint, x plus y equals to 500. So which means that both the value should be, x cannot be 500 because x is less than 400. So y should have some value. So in this case, the y value is 0. These two corner points are, revoked. It is not taken into consideration. We are only left with 1, 2, and 3 points. So when you we'll come back to the isoprofit line a little later. So we can take a look at the corner points, all the 5 points. Even though 150 comma 0 gives us minimum, but that's not within the feasible region. The reason I told you, the y value is 0. And if the x value is 0 and if we have y value of something, then that is also not considered for this. But luckily there's no such the corner points. But when the y is 0, it is not forming the solution. So it will be overruled even if it is giving the very less value when compared to the optimal value. 400 comma 100, when you substitute that in terms of objective function, we'll get 55 lakhs. Whereas the other 2 points like 200 comma 300 or even 150 comma 300, it will give us more points. Like 65 lakhs is the highest, the maximum of it, and a value of 60 lakhs is neither maximum nor minimum. And this x marks are not forming the solution even though it is lesser. And then 55 lakhs is the minimum value, and that is within the feasible region. And our optimal value is x equals to 400 and y equals to 100. So we need to send 400 tons to site x and just 100 tons to site y, right? So and it satisfies all the constraints, like x plus y equals to 500, 400 plus 100 equals to 500, and x is less than equals to 400, yeah, it is 400, and y is less than equals to 300, it is just 100 less than 300, and x should be given greater than 150, yeah, 400 is greater than 150. It satisfies all the constraints, and hence this is the optimal solution. Next, we talk about whether that particular thing is an optimal or not. We use a concept called iso-objective line. We take the objective function and we will represent in terms of x or y. For this example, I'll take it in terms of y. So y equals to, when you take y the other side, the z mean and 10,000x, and when you do it, you probably get minus 2 by 3x plus 1 by 15,000 z min. Minus 2 by 3x is the slope and 1 by 15,000 is the y intercept, right? So it is, when you substitute the value of 0 for x, we'll get y intercept of 1 by 15,000 z minimum. It's not maximum, I beg your pardon, it's minimum, right? That's a typography error. And once you do that, when we'll have a series, we will do it by trial and error. We know that it is 55,000. Let's type 40,000, 45,000 and so on. So 45,000, 50,000, 55,000, 60,000, 65,000, and that each will give ISO profit lines or ISO objective lines. In this case, it is minimizing. So we need to find out the value that these lines coinciding with the corner point, which is in the minimum location. Say this hits initially this corner point, and then there's another ISO profit line lesser than this, and this hits this, and there's another ISO profit line less than this, and this hits, and among these three valid corner points, this is the lowest corner points get hit by the ISO profit line, and hence our objective was, our optimal value is correct. So this corresponds to the values that will minimize the total cost of disposal and minimize our objective function. So that is how you probably take a look at finding the optimal solution, right? So in the next class, we'll take a look at the maximization case, which we will be maximizing the benefits in the waste management perspective. See you then. Bye bye.